Hello everyone. This is continuation of our last lecture on electrostatics where we discussed Gauss law and applications of Gauss law. We discussed on electrical field. The last topic which we discussed was electric field density due to a spherical cell, which was a conducting spherical cell which has charges on its surface, and we considered surface charge density to calculate the electric field intensity, right? So let's discuss for a solid non-conducting sphere, right? So, topic is electric field intensity due to solid non-conducting sphere. So, what is the difference between the last topic we discussed and this one? So, since last sphere which we discussed was a conducting sphere and charges were accumulated and distributed on the surface, right? But since this is a non-conducting sphere, whatever charge is given to it, it has charges throughout its volume, right? Since it is a solid sphere, right? So let me draw a diagram for you. So this is a sphere. It had a radius r, right? And from a distance r from this sphere, I need to calculate the electric field, right? Again, we have three cases here. When r is the point which lie outside this sphere, when r is a point on this surface, and when r is a point inside the surface. So there are three cases which we'll be discussing, right? Okay, so let's start with case number one. Case one. So before doing that, what is the concerned charge density for us? This will be rho, volume charge density, which is given by charge by volume, right? Okay, so what is the net charge? Let's say I'm calculating for case one, r is greater than r, so this will be my Gaussian surface, right? So what is the net charge enclosed by this Gaussian surface? You can say the charge is equal to rho into volume. So net charge enclosed, which is q in, is given by rho into volume of sphere is 4 by 3 pi r cube, right? Okay, clear? Okay, so now applying Gauss law here. Gauss law states that surface integral of electric field intensity is given by charge enclosed by epsilon naught, right? So E into area of this particular Gaussian surface is 4 pi r square, right? It will be given by what? Charge enclosed by epsilon naught, right? So E is nothing but charge enclosed by 4 pi epsilon naught r square, right? Same as it was for the conducting shell, right? So now we can place this charge enclosed and calculate the expression, which is nothing but rho by 4 pi epsilon naught r square into 4 by 3 pi r cube, right? So what it comes out? 4 pi will cancel each other. So it is rho r cube by 3 epsilon naught r square, right? So this is the expression for electric field due to a solid non-conducting sphere at a point r which is outside it, right? Clear? Now what if this point is at the circumference, which basically means r is equal to capital R, right? Then what is the electric field intensity is our case 2. So let's discuss case 2. Let me have this. Okay, maybe we can erase it from here and we can discuss case 2, which basically says r is equal to r, right? And how my diagram will look like now? The Gaussian surface. So this exactly is my Gaussian surface, this circumference, right? This is my Gaussian surface. The charge enclosed is still same, right? Now applying Gauss law, again same way. ds is charge enclosed by epsilon naught, right? So E into, I can now write 4 pi r square because r equal to r, which is equal to charge enclosed by epsilon naught. So charge enclosed by epsilon naught. So E is nothing but Q in by 4 pi epsilon naught R square, right? I can put the value of Q in, which is rho into 4 pi R cube by 3 into 4 pi epsilon naught R square, right? 4 pi will cancel each other, R will cancel each other. So what it becomes? R square will cancel each other. It becomes rho R by 3 epsilon naught. Clear? This becomes rho R by, my calculation is right, it becomes rho R by 3 epsilon naught, right? For the case where R is equal to R, right? Now, let's say this R is less than R and I need to calculate inside this sphere. What is the spherical, what is the field at this point or this point or this point, inside points. So for the third case, it is a kind of different case from these two. And in this case, the field inside will not be zero, since we have field inside it as well, and this is a non-conducting sphere and not a conducting sphere, because for conducting sphere charges will reside on the circumference and it won't contribute to field inside it, right? But here we will have a field inside it, and let's see what is the value of that. So case 3, right? Case 3. Case 3 means R is less than R. So this is the case. Let me redraw the diagram. So this is my sphere. The radius is R, right? And my point of interest is somewhere at a distance R from it, and this is my Gaussian surface, right? Now the charge enclosed by this Gaussian surface will differ from what we calculated in other cases, right? So what is the charge enclosed by this Gaussian surface, right? So you know charge is equal to this charge density into volume, right? So volume is changing here, isn't it? Volume is changing here. So charge enclosed will be what? Rho into, what is the volume? 4 by 3 pi R cube. Clear? Right. So we are discussing the case where the point lies inside this non-conducting sphere, which means R is less than R, right? So charge is nothing but charge density into volume of Gaussian surface, because this is only the charge enclosed and not the full sphere, right? Now applying Gauss law, integration ds is charge enclosed by epsilon naught. So this is nothing but charge enclosed. So E area will be nothing but 4 pi small r square. Charge enclosed is nothing but 4 into rho into 4 pi r cube by 3 epsilon naught, right? So now if you calculate 4 pi cancel out each other, r square cancel out, this will be rho r by 3 epsilon naught. So this is for the case r less than r, right? Okay. So let's keep all three cases and see how it varies. So we discussed electric field intensity is given by rho by 3 epsilon naught r cube by r square for a point which is outside the sphere, r greater than r. It is rho r by 3 epsilon naught for a point at the sphere, at the circumference, right? And for a point inside, this is nothing but rho by 3 epsilon naught, rho r by 3 epsilon naught for a point inside, right? Okay. So now if I plot it graphically, right? If I plot it graphically, how it looks like. So let's say this is the graph and I have three cases. This point is r less than r, like left of this point, right of this point is r greater than r, and this is r equal to r, and I'm plotting it between electric field intensity E and small r, which is the distance from the center, right? So for r less than r, this case, you can see the electric field intensity is proportional to r, right? Proportional to r. So proportional means the graph will look like a straight line till this point, right? At r equal to r, it will be a constant value, which is exactly this value, which is nothing but what? Rho r by 3 epsilon naught, right, at r equal to r. For r greater than r, now you can see this case, r greater than r case, here electric field intensity is nothing but inversely proportional to square of distance from the center. So the graph will look something like this, right? Okay, now you can, now you are able to relate how it varies from inside it is proportional to r, at circumference it is a constant value, and after that it will vary inversely, right? So graph between E and R will look like this, right? Okay, now next topic is, this is probably the last topic in this chapter, called electric charges and field. The topic is conductor, semiconductor and insulator, right? So you might have come across these terms in your junior classes as well. This is nothing new to you. So what is conductor, what is semiconductor, and what is insulator? So conductor, as the name suggests, conductor is something that allow the conduction to happen, right? So a conductor are those species or atoms or molecules which has free electrons, right? Right. So we were discussing conductors. So conductors are those substances in which electrons are loosely bonded to its nucleus, right? So I would say loosely bond means, let's say this is a aluminum nucleus, right? And we have an electron. You know, electronic configuration is 283 for aluminum, and we have 3 valence electrons, right? So these 3 valence electron, which is in the third shell, are loosely bonded to this nucleus, and if I apply some electric field or something, these electrons may redistribute themselves and they may be responsible for creating an electric field here, right? So conductor has free electrons, and these free electrons are responsible for its conduction, right? You know, you have seen wires used in homes of aluminum, copper and things, and you see that electric current easily passes through it. It is because of these free electrons because of which electric current can pass through a conductor. What about insulator? Let's say insulator, some gas or some plastic, anything it can be. Difference between insulator is, here the electrons are very tightly bonded, right? And even enough energy you give, this electrons won't be ejected from this nucleus, right? So these electrons are not responsible for conduction, right? Okay, now third case, which is semiconductor. So for semiconductor, by definition, you know, the conductivity lies between insulator and conductor, right? So what is difference in semiconductor? As of now, you can take a basic background, right? That this has a varying conductivity with respect to temperature, right? Temperature. So you see that at 0 Kelvin, you can see that this can act like an insulator, right? So for example, silicon is a semiconductor. So silicon has this nature, 4 bonds, sp3 hybridization, silicon atom. So at 0 Kelvin, you will see that all these bonds are tightly bonded, right? And there won't be any conduction. But if you increase this temperature, you will see that some bonds will break and this will conduct. You can see that this has behavior in between a conductor and insulator, hence it is called a semiconductor, right? And the behavior can be controlled using temperature, and there are other factors also which we will discuss in the semiconductors chapter in next unit, coming later units, right? Okay, so now what I said is conductor. So let's say there is a conductor, right? This is a conductor. So it is neutral. A metal, you know, metals are conductors, right? So it is neutral. There is no electric field here, right? What happens if I apply an external electric field called E to this conductor, right? What happens? So I said that this conductor has free electrons, right? This has free electrons. So free electrons will get attracted towards the electric field, right? So these free electrons will get attracted in this direction of electric field, right? Leaving away some positive charges, right? Now what happens is, because of this electric field, there is an electric field established here as well. Let's call this as E dash, right? You see the electric field direction is from positive to negative. So because of this external electric field, an electric field is established here because of the redistribution of charges, right? Now you can see this redistribution with time, it will increase, like the number of negative species here and positive there, the numbers will slightly increase, and this E dash magnitude will slowly with time, it will keep on increasing, and at a point, and there will be equilibrium point where all this redistribution will stop, when this E dash will become equal to E, right? And at that point you see the net electric field inside this will be E minus E dash, right? And which is 0. So you can see that net electric field inside any conductor is always 0, right? You can observe this. Net electric field inside any conductor is always 0. This is a very simple and observed expression. So even if I give any charge to this conductor, it won't go reside inside it. It will come on the surface of this conductor, right? Let's understand by an example. So let's say there is a conductor. Let's say there is a conductor. This is a conductor, right? This is a conductor, and this we are applying any external electric field to this conductor. So if I take any small volume from this conductor, any small volume from inside the conductor, we know that field through this volume is always 0, right? Flux is always 0. Field is 0 means flux is 0, which basically means the charge enclosed is 0, right? So net charge, if I pick any volume from a conductor, will be always be 0. There will be equal number of negative and positive charges. So any block if I pick from inside, the net charge will be always 0. So if I put any external charge to this, the charges will reside on the surface of it, right? Surface of it. Simple. Okay. So let's talk about a conductor which has a cavity, right? Let's talk about a conductor which, this is a conductor and this is a cavity, like a hollow space, something. So if I give charge to this conductor, the charge will reside on this outer surface, right? Outer surface. But let's say if I am giving a charge plus Q to this cavity, now what happens, right? If I am giving a charge plus Q to this cavity, and I know electric field inside a conductor should always be 0, and if I take a Gaussian surface, let's say this is the Gaussian surface S, so this Gaussian surface has a charge plus Q, and hence there is electric field, right, which violates what we just concluded. So this plus Q will indicate negative charges on this periphery, right? And now you can say that electric field inside this S is always 0, and this negative charge will induce equal amount of positive charge on the outer circumference, since the conductor overall is neutral, right? Okay. Okay, so we are almost done with this unit on electric charges and field. Now let's solve some of the numericals on this unit. So this is one of the numerical. Let's start with this. This brings quite into electric field, electric force, your understanding of mechanics from class 11th, the vector concepts, everything, right? So the question says, two identical pith balls carrying charge Q plus Q are suspended from common point by two strings of equal length L, right? Find mass of each balls if angles between two strings is 2 thetas at equilibrium, right? Okay, so there is a common point. Let's say this is a hinge. This is a common point. So from this common point, two identical pith balls are suspended, right? This has charge plus Q, this has charge plus Q, and angle between these two are 2 theta at equilibrium, right? Okay. So now aim is to find the mass of each ball. Both are identical, right? So let's say M is the mass of this one and M is the mass for this one as well. So what is the mass of each ball, right? So what are given conditions for us? The charge is given, which is plus Q. The lengths of string are given, which is L and L. And Also the angle is given, which is 2 theta at equilibrium. So what exactly is equilibrium? Equilibrium means a stage where net force acting on a body or a system is 0, right? So at this particular angle 2 theta, this system is in equilibrium. So net force on this and this will be 0. So let's take only one charged body, right? And what are the forces acting on it? So let's talk about this plus q, or any, let's say this plus q, right? So what are the charges, forces acting on this? So since there is a string here, so there will be a tension from this spring, right? String, sorry. There is a tension because of this string. And obviously there will be a force of gravity from earth, which is mg. Let's say this is fg, force due to gravity is mg. Now there is third force which is acting, which is because of this plus q on this one, which is nothing but electrostatic force, and it is away from this because both are of same signs, and this will repel this by electrostatic force, which is nothing but kq square by, let's say this distance is r, so r square, right? Okay, clear? Now what are unknowns to us? We don't know what is the value of tension, we don't know what is the value of this r, right? And we need to find the value of m. Okay, so before drawing a free body diagram and solving this, let's find out what is the value of r and other things, right? Okay, let me draw a perpendicular from this point. Okay, so this will be theta. Okay, since system is symmetric. Okay, so now you can say this is r by 2 and r by 2. You can say that sine theta is equal to r by 2 upon l, right? Clear? So r will be nothing but 2l sine theta. Clear? R is nothing but 2l sine theta. Okay, now let's draw a free body diagram and understand this question, right? Now you can see this tension, this is theta, this will be what? 90 minus theta, right? So tension has two components. So this component will be sine theta and this component will be cos theta, right? Since this is 90 minus theta, this is theta again, and this component is t cos theta, and component towards the left is nothing but t sine theta, right? Now you know this system is in equilibrium in both directions. Now you can easily calculate, but let me draw a free body diagram for you to explain, right? Okay, so this is a body, this has t cos theta in the positive y side, this has mg in negative y side, this has kq square by r square in positive x side, and this has t sine theta in negative x side, right? Now you can easily equate this force because system is in equilibrium. You can say that t cos theta minus mg is equal to 0, and hence t cos theta equal to mg. Similar, t sine theta equal to kq square by r square, right? Simple. Let me take the ratio. Let's say this is equation 2, this is equation 3. I'll take 2 by 3. So t will cancel out each other. Cos theta by sin theta is cot theta. Cot theta equal to mg by kq square by r square. So mg r square by kq square, right? Clear? Can I write it, if I put k equal to 1 by 4 pi epsilon naught, can I write it like this? mg r square 4 pi epsilon naught by q square, right? Clear? Now if I calculate m from here, right, what is m? M is nothing but m equal to cot theta q square by g r square into 4 pi epsilon naught. Now what is the new quantity? Theta was given to us, q was given to us, g is a constant, 4 pi is constant, epsilon. R we need to put from 1. R is nothing but 2l sine theta. So let's put value of r, cot theta into q square by g 2l sine theta square into 4 pi epsilon naught, right? Now you can easily calculate and find the value of m, right, which is nothing but q square cot theta by 16 l square sine square theta pi g epsilon naught, right? So this is the value of m, right? Clear? So let's move to next question. right? So next problem. So next problem states that a ball of mass 100 gram and charge 4.9 into 10 raised to power minus 5 coulomb is released from rest in a region where horizontal electric field of 2 into 10 to the power 4 Newton per coulomb exists. Find resultant force and where will ball be at 2 seconds. So at the end of 2 seconds, where will ball be, right? So let's draw a diagram before going to solve the problem. Okay. So there is a horizontal electric field which is given by this value, which is acting on a ball which is released from rest. Okay, so let's draw two parallel lines and let's say that horizontal electric field is from this to this, right? The value is 2 into 10 to the power 4 Newton per coulomb, right? This is the horizontal electric field, and let's say this is the ball. This has a mass m, charge q, you know, m is 100 gram, which is 0.1 kg. Charge is 4.9 into 10 to the power minus 5 coulomb, right? And it is released from rest. So I can also write the initial velocity is nothing but 0 meter per second, u equal to 0 meter per second. These are the given informations to us, right? So resultant force on the ball, we have to find the resultant force on the ball. So how many force is acting on this ball? So one is because of this electric field which is between these two, everywhere it is between these two plates. So there is an electrostatic force in this direction on the ball, which is QE, right? QE. And obviously gravity is everywhere. So one is gravitational force, which is nothing but mg, right? So there are two forces acting on this, right? And net resultant force will be somewhere here, Fr. You need to find what is Fr, right? Okay. So if I draw a free body diagram here, right? Free body diagram. So solving part A. So this is the ball. You have force, this electrostatic force acting here, the gravitational force acting here. The resultant is 90 degree, right? So according to vector law, what is the resultant force? Resultant force is nothing but under root Fg square plus Fe square plus 2 Fe cos 90. Cos 90 is 0. So it will remain nothing but under root Fg square plus Fe square, right? Okay. So let's calculate the value of Fg and Fe. So Fg is nothing but mg, m is nothing but 0.1 kg, and g is nothing but 9.8. So it will be what? 0.98 Newton, right? Fg. Electrostatic force is what? QE, right? So QE, Q is given as 4.9 into 10 to the power minus 5. The E is 2 into 10 raised to 4. So this is again nothing but 0.98 Newton. So if you find resultant force using this expression, this will be nothing but 0.98 root 2 Newton, right? This is the resultant force. And you can see this magnitude is 0.98. This magnitude is also 0.98. So you can easily say that this resultant will be equally angled with both, which is 45 and 45, right? Okay. Now the next part of question is what? So what is, can you solve and tell me what is the value of this force? This will come around something around 1 point, let's say 1.3 Newton, something around 1.3 Newton, right? Okay. So this is the resultant force, right? So next question is, we have calculated this as 1.3 Newton. Where will ball be at time equal to 2 seconds? So after a span of 2 seconds, where will ball be, right? So you know the trajectory of ball will be in this direction along the resultant force direction. So at the time 2 equal to 2 seconds, what distance it will cover, right? Okay. So you know, let's solve part B. You know, using equation of motion S equal to ut plus half at square, right? So to calculate this, I know u, which is 0. So this term will cancel out. Time is 2 seconds. I need to have acceleration, right? So we need to calculate acceleration. So acceleration according to second law of motion, F equal to ma. Acceleration is nothing but F by m. So now I can calculate the distance, which is half F by m t square. F we calculated in the first part of this question. So half into 1.4 by m is nothing but 0.1. Time is nothing but 2 into 2, right? So this will so what is the value now? This is 28 meters. So distance it will cover in 2 seconds is 28 meters, right? This solves this particular question. Let's move to the next one. Okay, so this is our third problem for today, which basically said two particles A and B having charges 2 microcoulomb and minus 4 microcoulomb are held fixed at a distance 20 meter. Locate the point on line AB where net field intensity is 0. Okay, so let me draw a diagram for this problem. So there are two charges at point A and point B. One is the magnitude is, let's say, Q1 equal to plus 2 into 10 to the power minus 6 coulomb. Let's say Q2 equal to minus 4 into 10 to the power minus 6 coulomb, right? These two are the magnitude of charges, and distance is 20 meter. 20 meter. Okay. Now we need to find on this line AB at which point electric field intensity is 0, right? At which point electric field intensity is 0. Okay. So you notice that these two charges are of opposite signs, right? One is positive, another is negative. Both are unlike charges, right? Both are unlike charges. I need to find at which point on this line AB, this line AB can extend in both the directions, right? So at what point the electric field intensity will be 0. So let's talk about point in between AB, in between A and B. Let's take any point in between AB, right? So electric field due to A, you know, it is away from A, right? At same point it will be because of B, it will be towards B. So this is an aiding electric field. Both electric fields are aiding each other. There is no opposition, and if there is no opposition, there is no point of cancellation and making field intensity to 0, right? For cancellation, I obviously need vectors in two opposite direction, let's say E1 and E2. When they becomes equal, I would say these two cancel out each other, right? But if you take any point between A and B, you see these both vectors are aiding to each other, which means there is no possible point in between A and B where field intensity is 0, right? So possible point can be towards the right of B or towards the left of A, right? There are only two cases. Now you can think analytically that since this charge is of higher magnitude and this charge is of lower magnitude, right? And if I pick a point towards the right, so electric field due to this will be very, very higher than electric field due to this, because this is of higher magnitude and this has less distance also. So this can never make it 0. So analytically you can say that only possible way to get a 0 electric field intensity is only the left of A, so that the field due to this the charge Q1 and field due to Q2 can balance out each other, right? So let's take a point P which is at a distance R from A1 and calculate what is the value of this R, right? Okay. So now field on P due to A is nothing but KQ by R square, which is KQ1 by R square, right? And which is in the direction towards the left, right? Or you can say minus I cap is the direction for this, negative X. Due to B, field on P will be what? It will be KQ2 by 20 plus R, net distance will be 20 plus R square, right? And since it is of negative, this is a negative charge, the direction will be in this side towards the right, and it is plus I cap. Net field is what? Net field is EPB minus EPA, which is equal to 0, and hence EPB equal to EPA, right? Clear? EPB equal to EPA, right? Okay. Now let's put the values. This is KQ2 by 20 plus R square. This is KQ1 by R square. Okay. KK will cancel out each other. Q2 is nothing but 4 into 10 to the power minus 6 coulomb. These all are magnitudes, right? These all are magnitudes. By 2 plus R square. This is nothing but 2 into 10 to the power minus 6 by R square, right? Minus 10 to the power minus 6, 2 and 2 will cancel. So 20 plus R square equal to 2r square. Now let's remove these squares. So 20 plus r will be nothing but root 2r. So r is nothing but 20 by root 2 minus 1, right? 20 by root 2 minus 1. You can calculate this value and this will be meters. So at this point on left of A, my electric field intensity will be 0, right? So this is a very good question. But what if these two charges are of same nature and these two are positive charge? Then that point may locate in between A and B as well, right? So let's change this question a bit. And let's change this question a bit. And let's say now the charges are like this is 2 into 10 to the power minus 6 coulomb and this is plus 4 into 10 to the power minus 6 coulomb. Now you need to locate the point on AB where net field intensity is 0, right? So this is a homework problem for you, right? We will discuss this in the next class and we will close for today. Thanks.